In this video here, we're going to take a look at Fermat's little theorem. So Fermat's little theorem is a useful tool that allows us to find least residues of powers quickly and to also solve some congruence equations involving powers. Now Fermat's little theorem states that if p is a prime number and a is any number not divisible by p, then a to the power of p minus 1 is congruent to 1 mod p, and also a to the power of p here is congruent to a mod p. And the two statements for the theorem above are equivalent, and you can use them without proof in an exam. So let's just examine then how we can use Fermat's little theorem to solve congruence equations. So let's just have a quick look then at how we can use Fermat's little theorem to solve congruence equations. Now, if we have to solve a congruence equation with a prime modulus, then we may be able to use Fermat's little theorem. Now, if p is prime and p does not divide a, then the GCD of a and p is equal to 1, right? They're co-prime. And in that case then, ax is congruent to b, mod p has exactly one solution in the set of least residues modulo p. So ax is congruent to b mod p, and let's just multiply both sides then by a to the power of p minus 2. If we do that here, then what we get is a to the power of p minus 2 times ax is congruent to a to the power of p minus 2 times b mod p. Now, using basic rules of indices here, the left-hand side would simplify to give us the following. So we get a to the power of p minus 1x here is congruent to a to the power of p minus 2 times b mod p. And now by Fermat's little theorem here, a to the power of p minus 1 times x here is congruent to 1 mod p. So therefore x is congruent to a to the power of p minus 2 times b mod p. So to summarize them, if a and b here are positive integers and p is a prime number where p does not divide a, then a to the power of p minus 2 is a multiplicative inverse of a modulo p. And then finally, the solution to the equation ax is congruent to b mod p is given by the following here. So x is congruent to a to the power of p minus 2 times b mod p. So in terms of an introduction here to Fermat's little theorem, we don't really need much more than that. It's not too heavy in terms of new content, that we're covering. Just, a few little bits here that we do need to be aware of. Okay. And obviously be able to use in an exam. So I think the best way to really demonstrate Fermat's little theorem is to just run through a couple of practice questions here. So let's just get started then with question 1. So let's just make a start then with question 1 here. Now for question 1 then, all we want to do here is find the least residue of 2 to the power of 100 modulo 13. And what I can see straight away here then is 13 is a prime number. And what that would suggest here then is Fermat's little theorem might be quite useful. Okay. So what I can do here then is use Fermat's little theorem. And what I obtain then is 2 to the power of 12 is congruent to 1 mod 13. Okay, like so. Now what I can also do here then is rewrite 2 to the power of 100 by using the basic rules of indices, right? So 2 to the power of 100 here is the same as 2 to the power of 96 times 2 to the power of 4. Okay, well 2 to the power of 96 here is just the same then as 2 to the power of 12 all raised to the power of 8 times by 2 to the 4. Like so. Well, 2 to the 12 here is congruent to 1 mod 13. So what I've got here then is 1 to the 8 times 2 to the 4. That's just 1 times 16 here. So we obtain 1 times 16. Now this is mod 13, right? So I've got 1 times 16 here, mod 13. Well, 1 times 16 is 16. So 16 mod 13 here is congruent to 3 mod 13. Okay. And therefore, in that case, then, what we can see here, so therefore the least residue then, so least residue So the least residue of, what do we have here then? So 2 to the 100. 2 to the 100, mod 13. Let's do it in a bracket. So mod 13 is 3. Okay. And there we have it then. So nice and straightforward. That gives us the solution to question 1. And then finally, to finish with here, let's just have a go now at the very last question, question 2. So for question 2 then, all we want to do here is find the remainder when 4 to the power of 500 is divided by 7. Now this here then is just the same as, let's just make a note then. So 4 to the power of 500 being divided by 7 is just the same then as 4 to the power of 500 mod 7. Okay. And again, what I notice here then straight away is 7 is a prime number. And again, what that would suggest here is Fermat's little theorem will probably be quite useful here. So by Fermat's little theorem then, let's just do that over here on the right. What I've got then is 4 to the power of 6 then is congruent to 1 mod 7. Okay. So 4 to the 6 then is congruent to 1 mod 7. So just like we did then for the first question here, what I now want to do then is rewrite 4 to the power of 500 just by using the basic rules of indices. Okay. So I've got 4 to the power then of 498, like so. So 4 to the power of 498 here is equal to 4 to the 6. So I get 4 to the 6 here to the power then of 83. Okay. Well, 4 to the 6 here is congruent to 1 mod 7. So what I've got here then is 1 to the power of 83, which is just congruent to 1 mod 7. Okay, so hopefully nice and straightforward there, just to get us started, like so. Well, in that case then, if we want 4 to the power of 500 here, let's just write this underneath then. So 4 to the power of 500 here is equal to 4 to the power of 498. So 498 times by 4 squared. Okay, just basic rules of indices here. Well, in that case then, what do we get? Well, this here is congruent to 1 mod 7. That's what we've just established here in the previous line. So I've got 1 times 4 squared. So that's 16 here. So this is congruent to 16, which is congruent to 2 mod 7. Okay, like so. And therefore then what this means here, so therefore then the remainder here, the remainder is this number here. So the remainder then is 2. Okay. So the remainder when 4 to the power of 500 is divided by 7 is 2. And there we have it. So that gives us the solution to the very last question here, question 2. And that brings us to the end then of this video here on Fermat's little theorem.